Great, thanks, Alex. Hi, everyone. I'm Brian. I'm a developer at Netflix working on the personalization data engineering team. And I'm very excited to talk to you today about a new feature being added to Iceberg, and that's the Kafka Connect Iceberg Sink. I hope you find this talk informative and interesting. So to get started, I wanted to give a quick overview of Kafka Connect. So Kafka Connect is a popular framework for moving data in and out of Kafka. It's very mature, having been around for many years, and it's a core component of the Kafka project. There are many different connectors available. Some of the popular ones include the S3 sink for writing data from Kafka to S3, Debezium source connectors for writing changed data capture records from relational databases to Kafka. Even Mirror Maker 2 is based on Kafka Connect. So it has a straightforward, decentralized, distributed architecture. A Kafka Connect cluster consists of a number of worker processes, and a Kafka Connect connector runs tasks on these worker processes. Connector deployment is configuration-based, so generally no new code needs to be written to run a connector. And once a connector is installed, you can just post to a REST endpoint on a worker to start things up. Kafka Connect also has a schema and data model abstraction. So as a connector developer, you work with this abstraction. And for the most part, you don't need to be concerned with dealing with different schemas and formats like Avro, JSON schema, and protobuf. What Kafka Connect is not is a full-blown stream processing engine. So if you want to perform joins, keybys, stateful processing, sessionization, and things like that, you'll want a stream processing engine like Flink, Kafka Streams, and so forth. So why do we want to have an Iceberg sink for Kafka Connect? There are already many ways to write data from Kafka to an Iceberg table. Iceberg has the well-proven Flink sink for some time. You can write data from Kafka to Iceberg using Spark streaming. You can even write data to storage with an existing Kafka Connect sink like the S3 sink and have an ETL step to get the data into Iceberg. But so in general, we want to make it easy for everyone to move data from Kafka to Iceberg, and that includes those with Kafka Connect experience and infrastructure. Some teams don't have the infrastructure or experience to run Flink or Spark streaming jobs, for example. And requiring complex new infrastructure just to write data to Iceberg is often too much to ask. In addition, Kafka Connect, being configuration-driven, can be very easy to use. So creating the Kafka Connect Iceberg sink opens up Iceberg to many who might not otherwise consider it. So as mentioned on the last slide, we want to make it easy to write data from Kafka to Iceberg, and we set some objectives to accomplish this with the Iceberg sink. Some of these features I'll go into more detail in a couple of minutes. So first, there's exactly one semantics. Of course, we don't want to lose any data, but we also don't want duplicate data, as dealing with dupes can complicate many data pipelines. We also want the sink to automatically evolve the Iceberg schema. So this means detect changes in the Kafka record schema and apply those changes to the downstream Iceberg tables. On a similar note, we want to have automatic table creation in cases where the destination tables don't already exist. And here again, we want to base the table schema on the Kafka record schema. We wanted to support routing Kafka records to tables based on a value in the record. So for example, write records to customer-specific tables based on a customer ID in the record. In addition, we wanted to centralize Iceberg commits using some type of coordination mechanism, because having many tasks, each committing to the same table, can result in metadata bloat and commit contention. We wanted to support both schematized and unschematized Kafka records. Using a schema is definitely desirable, but in the interest of making Iceberg more broadly available, we wanted to support those not using a schema as well. And finally, we didn't want to rely on any external systems other than the Iceberg catalog. So these dependencies, like other servers or databases, can add complexity and operational overhead. So we wanted to stick with Kafka Connect and the Iceberg catalog. And of course, you'll also need storage for your data files. In addition, we wanted to support any Iceberg catalog, not just one specific type of catalog. And just a quick note that there are some other Kafka Connect sinks for Iceberg, but they didn't achieve all of the objectives that we set out for here. And that's why we went ahead and developed a new one. So as some of you may know, the sink is currently in the process of being submitted to the Apache Iceberg project. Our hope is that it'll benefit from community involvement being a core part of Iceberg. That being said, the sink was originally developed by Tabular, and it has been available in open source since the middle of last year. So this version can be found in the Tabular GitHub repo. It's licensed under Apache 2.0, and this version is also available on Confluent Hub. The submission to Apache will be mostly the same as the tabular version. A few features present in the existing sink will be added after the initial submission is complete, like upsert and CDC support. But if you need the sink now, you can use the tabular version. Tabular is working on a plan to transition users to the Apache version when the submission is complete. So I'm going to cover how the sink works internally, and hopefully this will give you a better understanding of what's going on if you're running it, and hopefully you'll also find it interesting. So to achieve the objectives outlined previously, we decided on a distributed system consisting of worker components, a coordinator component, a channel for communicating between these, and only the Iceberg catalog as an external system dependency, along with file storage. So this diagram shows a very high-level overview of how the sink operates. On the left in purple, you have the source topics. In the middle in green, you have the Kafka Connect sink tasks. Each sink task runs a worker component. This shouldn't be confused with a Kafka Connect worker process, which is part of the Connect framework. The worker here is a component running inside the sink task. Workers are basically responsible for writing to data files. In addition, one of the sink tasks is elected a leader, and that one task is also responsible for running an additional component we're calling the coordinator. And the coordinator is responsible for performing commits to the Iceberg catalog. So we have a worker for each sink task and a single coordinator running in one of the tasks. And this is somewhat inspired by how the Flink sink works, where there are multiple write tasks and a single committer. And finally, we have a separate Kafka topic we're calling the control topic. And that's what we use as the communication channel between the tasks. So the worker components are responsible for writing the data, like I said. Not surprisingly, we're using the Iceberg Data API to write the data, and that gives us a few things like writing field IDs, which is important for Iceberg schema evolution features, capturing metrics for the Iceberg metadata, and support for various file formats like Parquet, Avro, and Orc. During the write process, workers convert the data from Kafka Connect data model to Iceberg rows, and during conversion is where differences between the record schema and the Iceberg schema is detected. And I'll cover schema evolution in a minute. Workers are also responsible for responding to start commit requests. So when a worker gets such a request, it's responsible for a few things. First, it needs to close out the files it was writing to. It then gathers the list of files written and associated metadata and responds with that information. And then finally, it commits the offsets corresponding to the data written to the source consumer group. The coordinator component is responsible for controlling the Iceberg commit cycle. So it initiates the commit at a configurable interval by sending out a start commit request to the workers. It gathers responses containing the file metadata from the workers, and then it commits that metadata to Iceberg tables involved. And currently, it's important that only one coordinator be running at a given time. And this is so we don't commit the same data to the same table more than once. And to ensure this, we have a leader election process. And whenever the source consumer group assigns topic partitions, we shut down the existing coordinator. We then wait for the source consumer group to become stable, and then we inspect the source consumer group metadata. We retrieve all the topic partitions being consumed by all of the tasks and order those lexicographically. We identify the first topic partition in the list and check if that task was assigned this topic partition, the first one. If it was, then that task is considered the leader, and we start up the coordinator. So we decided on using an internal Kafka topic for the communication channel between the workers and the coordinator. This was a natural choice for a Kafka-based system, such as a sink. Other systems like Kafka Streams and even Kafka Connect itself use internal topics. And this is in line with wanting to keep the sink self-contained and not have it rely on an external system. Because of this, though, you'll need to either enable auto topic creation or create the control topic ahead of time. You may also need to configure the topic authorization if needed. So for using topic allows workers to, so using a topic decouples the communication between the worker and the coordinator. So for example, if a worker can send a message before the coordinator is up, and the coordinator will receive that message once it starts. The topic acts as sort of a broadcast channel. So all workers and the coordinator consume from the control topic and receive all messages. And depending on the type of message received, a worker or coordinator will either act on it or ignore it. So there's a few types of control messages used in the commit protocol. So before I cover the commit protocol, I wanted to quickly introduce the message types. The start commit message is sent by the coordinator when it wants workers to finish up writing data and respond back with the metadata. The data written message is sent by a worker and contains files written for a given table. The data complete message is sent by workers after all data written messages for all tables have been sent by a worker. So if you're writing to multiple tables, you'll have multiple data written messages and one data complete message from a worker. The commit to table message is sent by a coordinator after it successfully commits to a table. And then the commit complete message is sent by the coordinator when it successfully commits to all tables. So again, here you might have multiple commit to table messages if you're committing to multiple tables, and then a single commit complete message for a commit. Okay, so let's quickly cover the commit protocol we're using. So at a given configurable interval, the coordinator sends a start commit message to the control topic. All workers and even the coordinator consume this message. So remember that all components read all messages from the control topic, but the coordinator ignores messages of this type. However, the workers receive the start commit message and they do a few things. So first, they complete the writes to all files for all tables it's writing to. The list of files written and the source offsets consumed is retrieved. The worker then starts a Kafka transaction on the control topic producer. In the transaction, the worker sends data written messages for each table and a final data complete message. The offsets are also sent to the transaction for the source consumer group. And then finally, the Kafka transaction is committed. So just to point out here, the worker is managing the source offsets rather than relying on Kafka Connect for that. If the worker got this far and successfully committed the Kafka transaction, then the worker assumes the coordinator will take it from here. And the worker is done at this point and proceeds to consume new data and write new data files and awaits the next start commit message. So moving along, all workers and the coordinator consume these data written and data complete messages that the worker produced. However, the workers ignore these messages, but the coordinator will actually process them. So first, the coordinator will buffer the messages coming in from all the different workers until it detects that it has received data complete messages from all of the workers. It detects this by ensuring all source topic partitions from the data messages cover all source topic partitions being consumed. Once all data complete messages have been received or a configurable timeout has been reached, the coordinator proceeds with the commit. And then the coordinator commits to each table and also sends out complete to table messages. When committing to Iceberg, the coordinator also sets a snapshot property that contains the offsets of the control topic. And I'll explain a little bit more in a minute how this is involved in achieving exactly one semantics. Finally, if all table commits are successful, the coordinator commits the control topic offsets to a control consumer group. And this is used as a low watermark during recovery. And then finally, also a commit complete message is sent. These commit messages are for information only currently. They aren't acted upon by the sink. So here's a summary how we're achieving exactly one semantics with this commit protocol. On the worker side, we send the data messages and update source offsets in a transaction. So data messages in the control topic are guaranteed to correspond to the source offsets. So in case of failure, the data messages are durably stored in the control topic and offsets in the source consumer group. On the consumer side, first recall that the coordinator committed a low watermark offsets to its consumer group. And this is the point at which all data messages were successfully committed to all tables. So when the coordinator starts up, it starts reading control messages from these offsets. Also recall that the coordinator commits to Iceberg with the control topic offsets as a snapshot property. So before committing to a table, the coordinator reads this property from the table metadata, and it skips any data messages with offsets before that point. It then performs the Iceberg commit with any new data along with a new property with the updated control topic offsets. So that's like a lot of information. So I'm going to cover a few recovery scenarios here to describe how we achieve exactly one semantics, and hopefully that'll give you a more concrete view on how it works in practice. So a worker may fail when writing data. For example, the connect process might die or be restarted. In this case, any data files that were in the process of being written are abandoned. Offsets for the source topic are never committed. Kafka detects that the source consumer is down and reassigns topic partitions to other members of the source consumer group. The data for these topic partitions is reread by the new consumers, starting from the last offsets that were successfully committed. The data lands in new data files, and these are eventually committed to Iceberg. So you'll have some leftover orphan files that were never committed, and you'll need to run some table maintenance to clean those up if you want to. So another scenario that might happen is a worker fails to receive the start commit message from a coordinator. So workers, when they start up, always start reading from the latest control topic offsets. The only message type workers currently consume and process is the start commit message, so there isn't really much need to replay those. If a coordinator sends a start commit message before the worker is up, then the worker could miss this message. In this case, the coordinator will wait to receive data from all workers, and eventually it's going to time out waiting, as it'll never hear from this one worker. This timeout is configurable. The coordinator will proceed with the commit without data from this worker and commit whatever data it has. And the worker that didn't submit any data will eventually submit its data in the next commit cycle. So what about coordinator failures? So say the coordinator starts the commit cycle, workers start sending back data, the coordinator starts buffering this data, but then fails before anything is committed to Iceberg. At this point, data in the buffer is lost, and also we're no longer running a coordinator anywhere. So in this case, the source topic partitions for the lost task are reassigned, and a new leader is elected as the coordinator. So whichever task is assigned the first topic partition. The new coordinator starts reading from the control topic from the low watermark offsets that were committed. So as a reminder, control topic offsets are committed only after all Iceberg commits to all tables succeed. So we know we don't need to read any control messages from before this point, so it acts as a low watermark during recovery. However, it is possible that some tables have control topic offsets that are more recent. So for example, if not all table commits succeed during a commit cycle, this could happen. So when committing to an Iceberg table, the coordinator first retrieves the control topic offsets from that table's metadata, and any older messages are skipped and only new data is committed. So another problem that might happen is that the coordinator could fail to commit to one of the Iceberg tables. So In this case, the commit buffer is left in place. Also, the low watermark control topic offsets are not committed. All of the data since the last completely successful commit will be processed to the next commit cycle. And as in the previous example, the latest control topic offsets in the table snapshot are used to filter out data that's already been committed to that table. So that's a brief overview of the commit protocol we're using. Now let's cover a few features of the sink. So table fan out. The sink supports routing records to multiple Iceberg tables based on a value in the record. To use this, you first set the name of the route field in the configuration. How to route fields to tables can be either statically or dynamically defined. In the static case, you map a table to a regular expression to match on in the configuration. And in the dynamic case, the route field is also used as the destination table. So you can actually specify the table name in your record where you want it to land. You might use this feature, for example, if you have a single topic for customer data and you want to write that data to a set of customer specific tables. In this case, you could set the route field to the customer ID. The sink also supports automatically creating Iceberg tables based on the Kafka record schema. The way it works, first off, as part of the routing process, the desired destination table name is determined. When initializing the writer for the table, we check if the table exists. And if it doesn't exist, the record schema is converted to an Iceberg schema. If there's no record schema, we infer it from the data. So once we have the schema, we call the Iceberg catalog to create the table. And this happens concurrently on any worker that detects that the table is missing. So we're calling create table on the catalog from all of these workers. And we rely on the catalog to ensure only one succeeds. Similarly, the sink supports schema evolution. So when converting a Kafka record to Iceberg, we detect any differences between the schema. So this includes any missing fields or changed data types. Differences are resolved to Iceberg schema updates, and then we call schema update on the Iceberg catalog. Again, this happens on all workers that detect differences, and we rely on the catalog to ensure only one succeeds. We support adding missing columns, and we also support certain type promotions supported by Iceberg, like int to long. And new columns are always added as optional in this case, regardless of what's defined in the record schema during schema evolution. Another feature of the sink is the valid through timestamp. So in addition to setting a snapshot property for the control topic offsets when committing to Iceberg, the coordinator also sets a valid through timestamp property. This is only set if the coordinator receives offsets for all source topic partitions being consumed. If not all topic partitions are represented, then no property is set. And this value represents the minimum offset timestamp across all source partitions consumed. So basically, this property is telling you that all data has been received up until this point, received and written down and written to data files. The valid through timestamp is also present in the commit complete message. So you might use this value, for example, to trigger downstream workflows. For example, a workflow may require that all data for a given hour has been processed. You could trigger the workflow by either reading from the control topic, or you could also poll for Iceberg snapshots or listen to Iceberg commits. And this feature assumes that timestamps are ordered in Kafka, so it's best to set timestamps to log append time for your Kafka topic to ensure this rather than create time. So control message serialization was modeled after how Iceberg serializes its metadata. So the message schema is defined using Iceberg types. The data is serialized as aggro using Iceberg utilities. And this allowed us to reuse the Iceberg metadata data structures. So Iceberg has data structures for data files, delete files, partition specs, metrics, and so forth. And we didn't want to duplicate this model and have to constantly keep it in sync with the Iceberg metadata. Another option we considered was to use cryo. But because our event data is persistent in Kafka, we needed to support schema evolution, which Cryo is not good at. Also, Avro serialization proved smaller as the number of data files increased. Because the serialization is somewhat specialized, we have a separate library for the message schema that can be used to deserialize messages in the control topic. And the hope is that we can use this in the future for any tooling that we build. So a quick note on zombie fencing, which we recently discussed in the community. There are some edge cases that can cause dupes. The best way for me to cover this is to give an example. So say a worker starts a transaction and sends some data messages and offsets. Now it enters a long GC cycle before committing to Kafka. The worker now becomes a zombie. If the pause is long enough, Kafka will think the source consumer is offline for this particular task, and it will reassign topic partitions. And as part of this, internally, Kafka also updates the consumer group generation ID as part of this rebalance. A new worker will then start rereading the records from the existing offsets. Now the zombie worker finishes its long GC cycle, comes back online, and finishes the Kafka commit. Meanwhile, the new worker also commits the same data, and we have dupes. So to prevent this, we pass in the source consumer group metadata when we commit to Kafka. And Kafka checks the consumer group generation ID. Because in our case, because the old worker has an old generation ID, it gets fenced out and its commit will fail. So now I'll cover a few slides on how to use the sink. So you install the sink like any other connector. You can copy the connector distribution to the plugins directory on all nodes in the cluster. You can also use the UI for your Kafka Connect platform, for example, Confluent Cloud or Amazon MSK. You'll want to turn on auto topic creation, like I mentioned, so the control topic gets automatically created. And if you can't do this, then you're going to need to create the control topic manually. And when you create it manually, you may also need to set up authorization on the topic. And just a note that if you want to, you can use the same control topic for multiple sink connectors. Generally, the volume on the control topic should be pretty low. Something outside the scope of the sink, but important to consider, is to set record keys on your source records and match this to any Iceberg partition keys in the destination tables. Doing this mimics Iceberg's hash distribution mode, which isn't supported by the Connect sink. In other words, it ensures that tasks read data for a subset of the partitions. And this in turn uses less memory and creates fewer files. So here's a simple configuration example. In this example, we're setting 2 tasks to run and read from a topic named events. All events in this topic will be written to an Iceberg table named default events. We also have some configuration for connecting to the Iceberg catalog, and in this case, it's a REST catalog. There are various ways to deploy a connector depending on your platform, again. So on Strimzy, you might have a Kubernetes manifest. On Confluent Cloud or Amazon MSK, you might use the UI. You can also use the Kafka Connect REST API. So here's an example using the REST API via curl. We're posting to the Kafka Connect REST endpoint on port 8083 on one of the Connect worker nodes, and it can be any of the worker nodes. So because the sink is config driven, the configuration could get very complex over time as we add more functionality. So to avoid this, we're relying on Kafka Connect single message transforms for more complex transformations rather than putting that functionality in the sink. And this allows us to modularize the functionality. So our goal is to provide a set of SMTs that cover common use cases. Some examples could be handling Debezium or Amazon DNS data. But if you want to write custom transforms, that will require that you write some code. So what's in store for Iceberg and Kafka Connect in the future? First, we want to finish the Iceberg submission. The next PR will be the coordinator piece, and that's the last major piece. And after that, it's mostly just the integration test and docs. The coding for this piece is done, so it should be posted any day now. And for anyone wanting to get involved and contribute, here are some future possibilities for Kafka Connect and Iceberg. In the sink, we could add a distributed coordinator where we distribute commits for multiple tables across multiple tasks. And this could help scalability when writing to several tables. Another is a pluggable coordinator where you can plug in an entirely different type of coordinator. So for example, one that supports using a server-side component for coordination rather than the control topic-based coordinator. This could be useful if you're building an ingestion platform based on the sink. Also, tooling such as reading from the control topic and making rollbacks easier, additional SMTs, dead letter queue or dead letter table support. So Kafka Connect has dead letter queue support, but it doesn't cover all of the error cases that we want. Also, coordinated table refresh and schema updates. So as I mentioned earlier, all workers currently call the Iceberg catalog to get table metadata or perform schema updates. So we could centralize this in the coordinator, which would put less load on the catalog. We could also allow for the valid through timestamp to be derived from a data field with some allowed lateness, perhaps. And then finally, we could add in the delta writers from the existing version of the sink once the initial Apache submission is done. In addition to sink enhancements, another possibility is to create a Kafka Connect source inspired by the Flink source. So this could read from Iceberg tables incrementally and produce records to Kafka. And this could be useful for backflow purposes, for example. So here are some resources if you're interested. There are the two GitHub links. You can reach out on the Iceberg Slack channel and the Iceberg mailing list. And also there are some great blogs out there on using the sink, so do a search for those. So that's it. Thanks for coming, everybody. Hope you enjoyed this presentation, and I hope to see you around in the Iceberg community. If there's any questions.
I just realized I was on mute. Thank you, Brian. That was fantastic. So now that everyone can hear me, I just want to say I'm opening it up for questions. I see lots of great questions in the Q&A stream, so we'll start with those. So first we have from Puchen Yang. Do you plan to support UDFs?
UDFs. I don't know, could I get more context around that? Like what are the UDFs? I mean, we'd support SMTs, which is, I guess, kind of sort of the equivalent to UDFs in the Kafka Connect world. So I think that would be probably the closest we would come to supporting UDFs.
Yep, awesome. Next question from Mikhail Sundel. Do I understand right that if I want to manage partitions, i.e. do a partition evolution, I need to do it with external tools? The connector will only be able to create the tables with determined partitioning and no more.
Yeah, currently the sink does not evolve the partitioning scheme. We can't really determine what the partitioning scheme is from the Kafka source record, so that information doesn't really exist in the source record to be able to apply that automatically downstream. However, I mean, you can evolve the schema in the partitioning in Iceberg, and then the sink will pick that up during the commit cycle or when writing data. It gets the table metadata gets refreshed every commit cycle.
Awesome. Next question is from Mike Williams. At what point do the workers persist data files? Do they wait to receive a commit request, or can it happen prior to that?
No, the workers are constantly writing data. So they're constantly reading from the source topics and writing to data files. When they receive a start commit request from the coordinator, then they close out those files, send back that metadata to the coordinator, and then continue reading from the source topics and writing data files. They don't wait for anything. They just keep writing data files. But there's this interim step where when they do get a request, they close things out, send the information back to the coordinator, and then continue on.
Okay. Our next question is from Puchen Yang. Could you talk about what challenges you have encountered in the area of schema evolution?
Yeah, I mean, probably the biggest challenge was how to coordinate it across all the different tasks. So, if you have, say, a large connector running with many tasks, all of them are going to be submitting these, schema changes to the catalog. So ideally, that would be centralized in the coordinator, but for now, we're using the catalog for that piece. So that was kind of a back and forth on how best to manage that. But we felt like at this point, it would be best for the catalog to control that.
And next question is from Arun Gupta. How frequently does a worker fail? Is there any risk of losing data?
No, there's never a risk for losing data. So in one of the scenarios I covered, I went over that, like when a worker does fail. What happens with Kafka Connect is Kafka Connect will reassign the source partitions to a different task. So a different worker will then be assigned the source topic partitions, reread the data from the last offsets, which were never committed by the worker that failed. And so that data will be reread and then written to new data files. You'll end up with some maybe orphaned files in that case. So you'll need to clean those up, but the table itself will be intact. It'll be correct, and you won't have lost any data or you won't have any dupes or anything like that.
Okay, and I'm going to combine these next two questions from Lazy Ann. So one question is just essentially one comparisons between Kafka Connect and using Flink, but two also just sort of like any guidance on sort of when to use one versus the other.
Mm-hmm. Oh, okay. Yeah, I mean, I would say like whatever infrastructure you have in place. So if you have Kafka Connect in place, then obviously the natural thing would be to use Kafka Connect. And if you have a Flink infrastructure in place, then use Flink and whatever your team is comfortable with using. That being said, I mean, the two aren't totally synonymous. So in other words, Flink has a lot more functionality. It's a full-blown stream processing engine. So you can need to do things like keybinds and sessionization and so forth. You're going to want to go with Flink. But if you're just simply wanting to take data as is from Kafka and write it to Iceberg tables, then Kafka Connect might be a good solution for you because it's a lot simpler and lighter weight. It uses less resources. So that would be my parameters, I suppose.
Okay, next question is from Brendan Cronin. Can this sink coexist alongside other means of writing data or upserting to existing Iceberg tables? If so, does every column need to exist in the data coming from Kafka? Or will it just write the same shaped rows, but with null values if the given field's columns are missing?
Yeah, so if you have schema evolution turned off, so I mean, schema evolution is optional, then it'll just set nulls for the columns that don't exist in the source records. And any additional columns will be ignored also. If you have additional columns in the source record, those will be ignored when writing to the Iceberg table if you have schema evolution off. Sorry, did that cover the question, or could you?
No, I think that did.
Okay.
And then next question is going to be from Stefan Svensson. I have had some problems using Avro union schemas with the Iceberg Sink connector. The schema in the Iceberg table created by the Sink connector is created with one column for every record type in the union schema. No problem with nested schemas where the schema, including complex types like structs, are created correctly and correctly reflects the message in the Kafka. Is there a known problem with Avro union schemas in either Kafka Connect or the Iceberg Sink plugin? And I'll kind of leave it at that.
Yeah, I mean, unions aren't supported in Iceberg. So we have to make a best effort when we're converting the Avro schema to an Iceberg schema, and that might not be ideal. So it's basically, I believe what's going to happen is you're going to end up with just a schema that's a union of all the possibilities in the union. I think that's what it'll end up looking like.
Okay, we should have time for a couple more. I see a follow-up question from Brendan Cronin. With schema evolution turned on, will it drop columns that exist in the table but do not exist in the latest messages from Kafka?
No, it doesn't. It never drops data, so it'll never drop a column. So you'll end up with that column will just always exist in the table, and it'll just be ignored going forward.
Awesome. And probably our final question from Geronimo Gill. Can the sink get into a constant rebalancing loop? If so, what can we do about it?
Constantly rebalancing loop. I mean, I don't believe so. I mean, that's basically the responsibility of the Kafka Connect framework and Kafka and the consumer group functionality in Kafka. So I don't think that's a problem. I haven't had that problem, but if you have had a problem like that, I would be interested to hear more about it and if there's any way for us to address that.
Okay, we're just about out of time, so I want to invite everybody to continue being involved within the Iceberg community by joining the Iceberg Slack channel, getting on the Iceberg dev list, and on the Iceberg Git. There's plenty of places to continue asking your questions and continuing learning more. And I want to say thank you again to Brian Keller for an amazing presentation.
Thanks so much. Glad to be here.
Thank you.